All right, so this is just a quick explanation of material from sections 4.1 through 4.2 about the exponential function. So an exponential function is a function where you take a certain value of a, which is going to be a number that is greater than 0 but not equal to 1. So that is the base of your exponential function, some number greater than 0 but not 1. And you raise it to a variable power. So we're calling that variable x. So this is as opposed to taking x and raising it to an integer power. We're taking an integer and raising it to a variable power. That's what makes it an exponential. So whenever you go to graph an exponential function, one thing you should be aware of is if you take 2 to any power, you will never get a negative answer out. So the graph does not exist down here where the y values are negative. The other thing to realize is if you take 2 to the 0 power, you'll get 1 out. And that gives you a point from which you can start graphing. And then you can imagine that as you raise x, you get it bigger, so maybe 2 to the first. That'll give you the point here. When you put 1 in, you get 2 out. When you put 2 in, you get 4 out. And you can see that this graph just starts increasing, and we say it's increasing exponentially. But on the flip side, when you put numbers like -1 in, you end up getting a half out. So that's right here. And then when you put -2 in, you get a fourth out. So we're getting even closer to the y-axis. And as you go on and on down the x-axis, making x smaller and smaller, your function approaches that x-axis. And it approaches it as if this x-axis is the asymptote that it's getting closer and closer to, but it'll never get there because 2 to the x can never equal 0, and it can never be a negative number. So it will just continue to get closer and closer. So the graph of y to the 2x has this shape to it, and it's a shape that you should learn and understand. And I mean, I know you can put it on your graphing calculator, but you shouldn't have to take the time to do that. If you graph 1/2 to the x, then you are taking a number that's greater than 0 and not equal to 1 and raising it to the x power. That's an exponential. However, there's another way to think about this, and that is 2 to the -x. Because 1/2 raised to the x is the same as 2 raised to the -x. So sometimes your exponential functions look like this, and the point that will not change is this point right here. Because whenever you put 0 in and you take a number that's not 0 and raise it to the 0, you're always going to get 1 out. But now what's going to happen is the larger that you make x, the smaller that this y value is going to be. When you put a 1 in, you're going to get a 1/2 out. When you put a 2 in, you're going to get a 1/4 out. So what this graph did on the left, this graph is going to do on the right. And what it did on the right, it'll do on the left. So your graph is going to go exponentially up on the left and approaching the x-axis on the right. So what a negative inside the exponent does, it's like a negative inside your function. And it does what it always does in algebra. It flips the graph on the y-axis whenever you put a negative inside your function. So on this next problem, we have an exponential, 3 to the x, and we're adding 2 to it. So hopefully you remember from algebra days that when you add outside the function, you move the graph up. So the graph that normally started here at this point 0, 1 is now going to start up here at the point 0, 3. When you plug 0 in, you get 1 plus 2. And not only does that point move, your entire asymptote moves, because now there's no way for this function to be any, or can't even be 2 or less than 2, because there's no way for 3 to the x to be 0. So you've not only moved the point, but you've moved the asymptote up. The graph is going to continue to do what it did up here in this first one. It's going to increase on the right and decrease on the left. But as it decreases on the left, it's going to approach the asymptote. And as it increases on the right, it's going to, so I'll put a 1 in, that'll be 3 plus 2, 2, 3, 4, 5. It'll shoot up like this. So adding outside the function moves the graph up. Adding inside the function, and in this case, inside the function means inside the exponent, moves the graph to the left. When you do things inside the function, things are backward of what you normally think. You think adding 1 would move to the right, but it moves to the left. The reason is, in order to get the number 1 out of this function, which is my point that I'm basing everything on, this point 0, 1, I have to put a negative 1 into the exponent. And a negative 1, when I add 1, will make this 3 to the 0. So this point that was usually here at 0, 1 is now here at negative 1, 1. I didn't move it up or down, so the asymptote is not going to change. And the function's still going to head down to that asymptote. And it's still going to head up on this side, but it's just doing it a little bit to the left. Putting a negative in front of your function flips it on the x-axis, because now everything that comes out of your function comes out as a negative. So it used to be that 2 to the x was always above the x-axis. It couldn't be 0 and it couldn't be negative. Well, now I put a negative in front. It still can't be 0, but it will always be negative. So the values coming out of this will always be negative. When I put a 0 in, I'll get negative 1. So that point that was up here flipped over the x-axis. And if I put a 2 in, I'll get negative 16, so way down here. So on this side, the function just gets more and more and more and more negative as x gets bigger and bigger. I should make that continue to go out and down. But on the other side, it's going to come up toward the x-axis, approaching it, but from the negative direction. It can never reach it because it can never be 0, but it can get close and closer and closer as you go. So that is what happens when you put a negative in front of your function. So when you do a combination of these things, then you have to sort of think through the process of, okay, it's flipped upside down, it's moved to the right, and it's moved down. Okay, so this negative is flips on the x-axis. This is moves to the right, because inside the function things are backward, and this is moves down. So what I usually like to do is figure out what happens when I put the value in here that makes negative 3 to that power 0. That's where I usually like to start. So in other words, if I put a 2 in for x, what am I going to get out? And putting a 2 in for x is going to make this 0. 3 to the 0 is 0. So, I'm sorry, 3 to the 0 is 1. It's going to make this 1. So that negative is going to make it negative 1. And I'm going to take away another 1, and I'll get negative 2. So when I put in 2, I get out negative 2. That moved to the right, and it moved down, but it also flipped on the x-axis. And so that's why I'm ending up down here. I used to be here, I moved to the right, I flipped on the x-axis, and then I moved down. And since it's a little hard to figure that out sometimes, the order of doing those things, using that trick of figuring out where that point is will help. The other thing is my asymptote also moved down. When I moved the point down, I moved the asymptote down. So my asymptote is now here. And because I flipped it over, I want to think carefully. If I put a number 3 in now, I'm going to get -3 minus 1. I'm going to be more negative. So this is the side where it's going down, and this is the side where it's approaching the asymptote, which I could see from over here. It's going to have the same shape as that because it flipped over, but it's also going to be moved. So that's a really quick review of exponential functions and how to graph them. On the flip side of your paper, you'll find that there's some other information that's probably familiar to you about how to deal with exponential growth, and maybe you've seen this before, logistic growth. I'm going to talk about that. These formulas should be very familiar to you as business majors, but we'll go through them as well. So there's this number E that we're going to be using in our business calculus class, and the only thing you need to know about E is that it's an irrational number, and it's approximately 2.718. I say approximately because, you know, irrational numbers just keep on going and going and going and never repeat and never end. So I couldn't tell you exactly what it is, but this is an approximation you could use if you need to. The fact that it's defined to be this limit is a bit beyond the scope of this course, but I will mention it when we talk about the derivatives involving exponential functions. So y equals e to the x. E is a number that's greater than 0 and not equal to 1. So this is an exponential function. It'll have the same type of graph as the previous one. You put 0 in, you get 1 out. It continues to increase without bound to the right. So when you put 1 in, you get a little more than 2 out. Or a little more than 2.5 out. Increasing without bounds. On the flip side, remember it decreases toward that x-axis, but never gets there. Not many things in life grow without bounds. Most times things don't grow without bounds. For example, population. If you imagine that you have an island and you have a lot of bunnies living on that island and they continue to have babies, they cannot continue to have babies and increase their population without bound, because not only will they run out of space, they'll run out of food, and there'll be something on that island that's going to limit their population growth. And because we have situations like that, a more appropriate model for a lot of growth that we're going to use is called logistic. And the way a logistic growth model works is you have an exponential part to it. But if you imagine that your t is what we're going to usually call x, so we're going to imagine t being like time. As time gets bigger and bigger and bigger, or as we move through time, this part of the exponential, since it has a negative exponent, is in the denominator. And as that exponential part gets bigger and bigger and bigger, this fraction gets smaller and smaller and smaller. And there's a limiting value to this entire function of this going to 0 would lead the limiting value to be a over 1 plus 0, or a. So there's this asymptote on your logistic function that you cannot pass. You cannot go past it. The bigger t gets, the closer you get to it. The other thing is if you plug 0 into your function, then this part will become the number 1, and you'll just be at some point, depending on what your A and your B are in your exact equation, some point on the y-axis, and your growth is going to grow, but it's going to have a limiting value to it as it grows. And on the flip side, it's going to decrease toward the y-axis just like our other graph does. But this type of growth, where it's not growing without bounds, is going to be more appropriate in a lot of our problems. So that's what you need to know about exponentials. The other part of 4.2 is interest. And there are some formulas that you're going to be responsible for interest. However, you do not need to have them memorized. They will be on the test. You need to know that if you are trying to figure out a balance in the future, so your new balance, what you're going to have in the future, you're going to use this formula. This is the formula if you're going to compound a certain number of times a year. Like a bank account gives you interest every month, and if that's the case, then N, which tells you how many times in a year you compound, would be 12. Most of the time when you think about it, a bank account, that's what you think. You compound monthly, N would be 12. T is always going to be the time that you're investing in years. And R is always going to be your rate. So if you have an annual rate of interest, every time you compound, you're going to get a portion of that rate. And that's what R divided by N is doing. It's taking the rate for the entire year and splitting it up into pieces, depending on how many times you compound in a year. P is what you invest, and A is what you get out. So hopefully that you've seen that before, but just a quick refresher. If your investment compounds continually, and what they mean by that is it's not every month, it's not every week, it's not every day, it's not even 3 times a day, it's not even every second, it's even faster than that. It's a hard thing to imagine, but you're just continually compounding and you can't even put a time limit on it. Then you would use this formula. And you notice there N is not a part of it because N is infinite. It's not a value that I could plug in. So this is its own formula for continually compounding. The present value and the new balance formulas are just reverses of each other. In this formula, I'm plugging in P and figuring out what comes out of my investment. In this formula, I'm trying to figure out what I need to invest to get this much out in the end. All they did to go from this formula to that formula was divided both sides by this piece of the formula. So it's nothing new, it's just a new way of thinking about it if you're trying to figure out what you want to invest instead of how much you're going to get out. And the middle one, effective interest rate, oftentimes you may be looking at investments that not only have a different rate, but a different number of times they compound. And so then it's hard to compare them because it's not like apples to apples. I may get 3% in this investment, but I only get my interest quarterly. Whereas another investment, I may get 2.95%, but it may be compounding monthly. So I want to have a way to compare them on a level playing field. That's what the effective interest rate does. It takes out the number of times you compound and lets you look at the interest rates to be able to compare which is a better deal for you. So these are the formulas you'll need to be able to use. Again, not memorize, but an example would be if an amount earned from $20,000 invested, that means that has got to be my P, because P is what I put in, or my principal. 4 years would be my T, and R would be 0.04 because R is always written as a decimal. So to compound monthly, what you would do is you would plug into this formula right here, and A would be your $20,000 times 1 plus, and then you take your interest rate and you divide it by the number of months in a year, because compounded monthly means N is 12. And then your exponent becomes that N times the number of years that you're going to invest, which is 4. And I don't have my calculator with me, but if you check the answers on Angel, you can make sure that you're plugging it into your calculator correctly and coming up with the right answer. Compounding continually, I would take my principal times E raised to the 0.04 times 4. And again, there's no N involved because doesn't have a certain number of times I'm compounding. And again, I don't have my calculator, but if you calculate that, you can check the answers on Angel if you're concerned. Effective interest rate. So what's the difference if I get 5% compounded quarterly versus continually? How much of a difference does it make? That's what effective interest rate can tell me. So here I'm going to take 1 plus the interest rate I have. Quarterly means N is 4 times a year. And then I'm going to multiply in my exponent is going to be that 4, and I'm going to take away a 1. And that's what my formula tells me to do. When I calculate this, it'll give me a rate that I can compare to the effective interest rate if I compound continually, which is E to the 0.05 minus 1. And in comparing these two numbers, I'll be able to see how much of a difference does it make if they offer to compound continually for me versus just every quarter. And then finally, present value. For present value, I'm trying to figure out what I need to invest right now to get a certain number out in the end, or when my investment is over. So in this case, 20,000 is not P, 20,000 is A. It's what I want to have after 5 years. And so I can figure out what I need to invest in these two different situations to get that. And I'm going to use this formula here for present value, meaning I'm going to take that 20,000 and divide it by 1 plus the interest rate, which in this case is 3%, divided by N, which if I compound semi-annually is 2. And that is also raised to the 2 times 5 because T is 5. As opposed to compounding continually, now I'm going to use this formula and take my 20,000 divided by E to the 0.03 times 5. And I'll be able to see how much of a difference it makes, what I need to put in to come out with $20,000. How much does that compounding change my balance? So hopefully that's helpful for you, and you'll be able to complete the homework assignment, and I will see you next class.